A single collision in deep space can forge more gold than you could ever imagine. We're not talking about a few bars. We're talking about hundreds of Earths made entirely of pure gold. A 1.3-second delay. That's all it took. After traveling 140 million years across the universe, a tiny gap between two signals rewrote everything we thought we knew about gravity. In August 2017, two detectors picked up a signal that lasted nearly 2 minutes. At the same time, a gamma-ray telescope caught a flash from the same direction. What they found was something no one had ever seen before. This is the story of the first kilonova. On an afternoon in August 2017, gravitational wave detectors called LIGO and Virgo picked up the trace of a signal. This wasn't the first time. They had already captured gravitational waves from black holes and neutron stars before. But this time, something was different. Normally, the waves created by merging black holes were extremely brief, lasting less than a second, like a burst that comes and goes in an instant. But this signal lasted nearly 2 minutes. That was seriously strange. If even an event as incredibly energetic as merging black holes lasted less than a second, then what on earth was this? The researchers at LIGO and Virgo immediately went on high alert. They sent an urgent message to astronomy communities around the world. But at that very moment, the Fermi Gamma-ray Space Telescope had already sent a similar alert to experts. It was a short gamma-ray burst. Both a gamma-ray burst and a gravitational wave had been detected at the same time. Everyone was trying to figure out what was happening. Eventually, all the data pointed to one thing. At that moment, astronomers were witnessing something never seen before. A kilonova. A kilonova had never been detected before. As far as we knew, it wasn't as powerful as a supernova, but it was far stranger, far more exotic. One of the strangest events in the universe, and it was being observed for the very first time. When this was caught through both gamma-ray bursts and gravitational waves, you can imagine the excitement among every astronomer and amateur observer out there. You know how cats go wild when they hear the lid of their favorite treat being opened? It was exactly like that. They were literally running. Fortunately, we live in such an incredible time that within just 11 hours, the direction of those signals was pinpointed, and we captured the first ever visible light photograph of a kilonova. The days, weeks, and months that followed were consumed by this single event. Images were captured across every wavelength of light. Within 2 months, hundreds of academic papers were ready for publication. After that, an entire scientific journal was published dedicated solely to this one event. Everyone who observed it, photographed it, or wrote anything about it had their name in that journal. Roughly 4,000 people. Nearly a third of the entire global astronomy community. So now you understand the scale of what we're talking about. But what exactly is a kilonova? Let's start by understanding that. In the life cycle of stars, we observe events like novae, kilonovae, supernovae, and hypernovae. Each one is a massive event with its own specific causes and consequences. But each one also produces fascinating results. For example, the trace amounts of gold and heavy metals in your body. Yes, there's gold inside you. It comes from events like these. We'll get to that in a moment. A kilonova is 1,000 times more powerful than a nova, but not as bright as a supernova. It's an incredibly violent event, which makes it incredibly difficult, especially since it's also extremely rare. Because kilonovae are all about neutron stars. These neutron stars are the remnants of stars many times more massive than our Sun, born through a process that begins with the crushing of iron in the core of a star on the brink of a supernova. But this compression is so extreme that the entire weight of a giant star crushes down onto the iron in its core, forcing electrons into protons, turning everything into neutrons. What you're left with is a giant marble made entirely of neutrons. Beyond this point, no further compression is possible, and for a brief moment, the gravitational pressure eases. And that's actually what triggers the supernova, because the collapse suddenly reverses into an explosion, and a massive supernova is born. After all that chaos, depending on the mass, either a black hole forms or that neutron marble survives. We call that marble a neutron star. Neutron stars are genuinely some of the most exotic objects in the known universe. Sometimes they can feel even stranger than black holes. We're talking about something with dozens of times the mass of our Sun, squeezed into a space the size of a small city. That's absolutely mind-bending. And all that mass spins like a restless child. These things can rotate thousands of times per second. A cosmic disco ball that would put any dance floor to shame. And as if that weren't enough, their gravitational pull is so strong that they can trap light itself in orbit around them. Yes, an object whose satellite is light. One of the most attractive objects in the universe in the most literal sense of the word. Now, let's take two of these bizarre objects and smash them together. Don't try this at home, though. The results might not be pleasant. You'd end up with enough gold and precious metals to make all of humanity rich beyond imagination, but you wouldn't survive long enough to enjoy it. Anyway, let's get to what would actually happen. The result would be a kilonova, two neutron stars colliding in a spectacular display of cosmic violence. The outcome? Sometimes, strangely enough, a larger neutron star survives. Sometimes a black hole forms. And sometimes they annihilate each other entirely, as if neither had ever existed. A colossal wreckage. Don't expect a spectacular light show from this event, though. There isn't much material left to emit light. These stars already spent most of their energy during the supernova that created them. The light that does appear is mostly the result of radioactive decay in the elements produced by the collision. Even before 2017, we theorized that neutron stars could collide. We had observed some short gamma-ray bursts, but we didn't fully understand what was causing them. We suspected neutron stars were involved, and that their mergers would produce massive gravitational waves. But we couldn't be sure. We had never caught one in the act. After all, these events are estimated to occur only once every 100,000 years. Supernovae are a different story entirely. A few happen every century. Compared to kilonovae, they're practically routine. Now, let's get back to the gold story. Kilonovae play a crucial role in the chemistry of life itself. We owe most of our elements to these destructive events. Every cloud has a silver lining, as they say. In the first few minutes of the Big Bang, all we got was hydrogen, helium, and a tiny bit of lithium. That was it. But hydrogen and helium are the building blocks of everything. They form stars, and those stars are factories, forging carbon and oxygen in their cores. And in the massive stars, the ones that die and scatter their materials across the universe so new stars and planets can be born, the fusion goes further: silicon, magnesium, all the way up to iron. But iron is the end of the line. Stars simply cannot produce anything heavier this way. So what do? They explode. Yes, and in the incredible energy released by that explosion, even heavier elements are born. To become stronger, you have to endure greater destruction. The more you're crushed, the more powerful you become. Fear the power of those who have been broken. But supernovae alone can't produce enough of the heaviest elements to fill our periodic table. For that, we need something else. And that's where the Kilonova steps in, like a specialist manufacturer entering the market. Even though they're less violent than supernovae, they have exactly the right combination of energy, density, temperature, and timing to easily produce every heavy element on the periodic table. True experts of their craft. High-energy neutrons scattered across the universe craft gold, silver, platinum, and xenon with exquisite precision. A truly magnificent producer. So, if you own any gold jewelry, take good care of it, because there's a very good chance it was made from material produced in an event just like the Kilonova we observed in 2017, or possibly that very event itself. And we're not talking about enough gold to make a few necklaces. A single kilonova can produce a gold reserve equivalent to hundreds of times the mass of Earth, an incredibly efficient cosmic forge. Think about that. Hundreds of Earths made of pure gold. Isn't that absolutely wild? But that's not all. The kilonova we discovered in 2017 revealed another treasure: insights about gravity itself. As far as we understand, gravitational waves travel at the speed of light. But general relativity isn't our only explanation for gravity. As magnificent as it is, it's not enough. It has gaps. At the singularity of black holes, general relativity breaks down completely. At the event horizon, it throws up its hands and says it can't help. The same goes for the earliest moments of the Big Bang, or dark energy accelerating the expansion of the universe. There are serious gaps. We need to improve and modify general relativity, and scientists have been working hard on exactly that. And some of them believed gravitational waves might not actually travel at the speed of light. But the gamma rays from the kilonova we detected arrived 1.3 seconds after the gravitational waves. Don't underestimate a 1.3-second gap in an event that happened 140 million years ago. Small discrepancies have rewritten the laws of physics before. That 1.3-second delay was the time it took for the light to escape the gravitational pull of the event. Gravitational waves weren't affected by this, so they didn't experience any delay. Which means gravitational waves really do travel at the speed of light. After this discovery, every scientist who had been trying to modify gravity from this angle had to put down their pens and start all over again. But something beautiful also emerged from this event, a concept called multi-messenger astronomy. We're talking about layered observations. When you look at the same event through different lenses, it tells you completely different stories. Gamma rays show you a few seconds after the event. Gravitational waves show you the exact moment. Electromagnetic observations reveal what happened in the weeks that followed. And like a massive team effort, you combine all these pieces of information to build a complete picture. Multi-messenger astronomy is truly one of humanity's most meaningful scientific endeavors. We're essentially a group of people watching nature's own experiments unfold in its cosmic laboratory and trying to make sense of what we see. And we're incredibly lucky to witness this beauty. But as always, until we meet again, I'm glad you exist. Take care.